Hi, good morning. I'm Jianshen. I'm a Ph.D. student from UC Santa Cruz, and today I'm going to talk about use of storage devices. My advisor is Carlos Maltzahn. In this presentation, I would like to start with the introduction of uses of storage devices, the background and motivation of it, and especially how different motivators that eventually lead us to this idea. And followed by that, I will discuss my research plan for this project, including the benefits quantification, uses of storage architectures in the network. And I will also discuss some of the challenges that we may have along with these items. For the background and motivation discussion of uses of storage devices, I will follow this diagram block by blocks. As you can imagine, the problem starts with the big data. More and more data are generated by different clouds, edge data centers, and all kinds of endpoints, for example, IoT devices. In an IDC report published in 2018, the size of the global data sphere would reach 175 zettabytes by the end of 2025. While storing data could be a problem, it actually created a great opportunity for different companies and own up the data to get insights and make profit from the data. Therefore, the machine learning applications and the AI related applications are becoming more and more popular. As you can imagine, the AI market size relying on these applications are growing year by year quickly. And according to this report by Omdeard, published in 2019, the annual revenue created by the AI technology will reach more than $120 billion by the end of 2025. The need of processing such a tremendous amount of data requires significant CPU horsepower. However, we have seen a breakdown of data scaling. The multi-core approach hits the end of store, and people has already started to predict that the Moore's law is ending, and there will be no more performance improvement provided by the future CPU, probably. And the problem is that is there a road forward? Two famous scientists in this area. One is John Hersey from Stanford, and the other is David Passon from Berkeley. Both of them together predicted that the future would be domain-specific architectures. This is really true. We have seen this GPU has already taken over the tasks that require multiple parallel processes from the traditional CPUs. And the TPU is also the same case, which is developed by Google, and it has taken over those matrix processing tasks for deep learning applications from traditional CPU. And for more recently, we see that the DPU or data processing unit, it is already started to taking over the network packet processing or storage request processing from the host to reduce the resource consumption of the host. While the semiconductor scaling has slowed down, the storage device performance is skyrocketing. The innovation of storage device performance with technology such as the MRAM, ReRAM, phase change memory, the VRAM, these technology actually create a solid performance engine to continuously push forward the performance of storage devices. And we have seen that the performance improvement in storage devices has already exceeded the performance improvement in CPU and DRAM. And not just that, we see that the storage interface is becoming the bottleneck of accessing storage performance from the device. With this trend, in the traditional storage architectures where the data need to move to the host computing resources, the CPU memory, in order to get the data processed, the cost of the moving the data in such a way is becoming more and more expensive. And specifically, the requirement of CPU bandwidth per device and the requirement of the DRAM bandwidth device are both increasing. To tackle this problem, the industry is starting to build computational storage devices where some of the data processing tasks right now can be done within the device, thus effectively reducing the host resource consumption while improving the efficiency. On the other hand, in a different line, we know that application performance requirements are always changing in different between different applications. But also the same application could have different performance requirements while it is evolving. But traditionally, when we map these performance requirement onto the hardware resources may not be such a difficulty because we only have a limited resource type to choose from. But right now we are not just the traditional resource type, but also we have the GPU, TPU, FPGA, things like that that would eventually complicated how we can map those performance requirements to hardware resources. And if we continue to move this requirement to continue to map this requirement to traditional server boxes that provide limited flexibility in terms of changes of performance requirement, it would inevitably result in resource underutilization and inefficient resource provision. In an IDC report, it found that in most enterprise data centers, the infrastructure has about 55% of the computing hour and storage capacity remain to be idle. And also, there are about 70% of the engineer has reported that the efficiencies in the time required to provision compute and storage resources. To tackle this problem, the industry started to think about disaggregating the resources where different resources types are organized in different pools and such that the system of different performance can be composed at runtime by picking up different resources types from different pools. However, with these two chains, they basically direct us to disaggregate computational storage devices. Without further optimization in terms of the storage architecture, we won't be able to fully leverage the benefits from these two chains. And so therefore, our idea is that to enable collective acting from computational storage devices. In other words, we would like the computational storage devices to be able to actively initiate communication with the other computational storage devices. With this capability, computational storage devices would not just be able to handle tasks that traditionally are considered to be valuable, for example, the filtering and projection functions from the database systems, and the compression function, data passing function, and the cryptography functions, but also right now can handle the functions that do need peer-to-peer communications between different value domains. For example, the redundancy function, the value management functions, and load balancing function. All these functions are traditionally require the data traffic between different hosts. We believe this is a new design space for storage system that can offer comparable efficiency at a lower cost because just like simple ends can collectively accomplish complex tasks, for example, to build house and search for food. Simple storage devices could collectively accomplish tasks that non-individual storage devices is possible to do. The similar idea is also captured by the Metcalfe's law, where it states that in a system that composed of n interconnected devices, the value of the system is proportional to the square of the number of devices in the system. In this case, the device will be the users of storage devices. Therefore, in summary, the idea of users of storage devices is built on top of the two chains while allowing devices to act collectively. And this is basically the figure that illustrates the idea of the users of storage devices. First, as I mentioned, the different users of storage devices in the cluster can actively initiate communication with any of the other users of storage devices in the cluster through the full cross-port network. And also different devices could be different domain-specific hardware. They could have different functions running within it and could provide different data access APIs to be called by the clients. And storage devices with similar capabilities could also be organized in a classes, such that they can collectively provide functions, specific functions to clients. Since these devices have computing, storage, and P2P capability, traditional hosts could be eliminated from this picture, therefore effectively addressing the host attacks and bandwidth mismatching problem caused by fast storage media. Now let's get into my first item in my research plan, benefit quantification of functional floating. Previously, we proposed a methodology called MIBU-based measurement methodology. However, this methodology have several limitations. To understand what we want to move forward, please allow me to have a quick introduction for this previous methodology. In order to compare whether the function should be running on a general purpose server or on an embedded storage device, we need to have a reference point for the performance comparison, because these two computing platforms are really different. And so we choose the storage media and the given workload that runs on the function, and we encapsulate these two factors into a new performance metric. We call the metric to be media-based work unit, or MIBU. To understand how we use this new metric as the reference point, imagine that we have a workload, and the workload is essentially the data access function calls, a collection of data access function calls, and we drive this workload onto the platform that runs the function that we would like to upload it to the storage device. In this process, we can evaluate the throughput of the workload. Now, if we can ensure that the limiting factor, the only limiting factor of the throughput, is the capability of the storage device, not bottlenecked by the platform CPU or the bandwidth of the system, but just the bandwidth of the storage device. And so this throughput right now essentially becomes a performance characterization for the given workload running on the specific storage device. Therefore, we define the throughput in this iteration to be a media-based work unit, or MIBU. With this definition, we can evaluate how many MIBUs that different platforms can generate, and then calculate the platform efficiency by dividing the cost of the platform by the number of MIBUs that the platform can generate. And similarly, we can also calculate the power efficiency and the space efficiency. With this platform efficiency numbers, right now we can compare different platforms apple to apple, and eventually we can answer the question regarding whether the function should be running on a general purpose platform or on a specific storage device. If you understand this is the MIBU-based measurement methodology, this methodology actually imposes the following assumptions. First, it assumes that the workload should be reproducible, because we need to evaluate the how many MIBUs that different platforms can generate, and therefore we need to make sure the definition of the MIBU remains to be consistent. And also, this methodology didn't explicitly answer the question regarding how we can actually evaluate a function if the function do require P2P communication. And finally, this methodology is essentially a throughput-based benefit quantification methodology, while in reality, the performance of the system is multidimensional, including not just the throughput metric, but also the latency and some of the other metrics such as availability. Therefore, we want to move forward this methodology to account for not just the offline evaluation for those reproducible workload, but also for those online evaluation for the online dynamic workloads. And especially with like the methodology can explicitly specify how to evaluate the function if the function do require data traffic between different file domains. And finally, we would like the benefit quantification with this methodology, not just based on throughput, but also can account for the other performance metrics, including latency and availability. So previously, we just evaluate the benefit of uploading using the key value workload. But eventually, we would like to evaluate more of some of the other interesting workload, including the tabular data transformation workload, because could be efficiently handled by some domain-specific hardware. And so to evaluate the performance of online workload on different platforms, we may need to create a model for prediction. In order to collect the data for the model and build the relationship of the workload performance on different platforms, we may need to chase and replay the workload. Well, it sounds simple, but actually it may come with a couple of difficulties. First, when you chase the workload, we need to make sure the overhead of the chase is small as possible. Still, this is a hot topic in recent research literature. And also, the I/O operation actually have dependencies with each other. In order to faithfully replay the workload on different platforms, we need to actually precisely capture and record the dependencies in the I/O operations. Even though we can finally produce a precise chase for the workload, when we get into the replay phase for the workload, we still need to consider the question regarding how fast we should replay the workload. If we replay the workload at the original speed, we may end up with underestimated the test platform. While if we choose to replay the workload as fast as possible, we may also end up with unexpected high I/O latency. To create a model for prediction, there could be multiple difficulties as well. Some model tries to reduce the complexity of the model by tailoring to specific systems or workloads, such as having assumption of the size of system. But for the benefit benefit quantification of floating functions to users or storage devices, we just don't want to have any assumptions about the size of the system or what kind of workload should be offloaded to the users or storage devices. Therefore, we would prefer a model that is system and workload agnostic, and typically that would require some machine learning technologies, right? And so, in this process, we will need to select a set of features from the collected data. If the size of feature set is too small, we may not be able to precisely capture enough information from the collected data. While if the size of features is too large, then we may end up with overfitting problem for the resulting model. And because this is a system and workload agnostic model, we may need to collect the data from different system and workload configurations, and therefore the complexity of only the data collection phase is the dimension of features times the dimensions of the workloads times the dimensions of the system, and this is really high complexity and may end up with may result in a significant time spent in collecting data. And finally, we still need to consider how to evaluate the models that can best leverage our data. For the benefit availability of using embedded storage devices for storage systems, we have done some work in the context of edge. And so, because edge infrastructure is usually deployed on remote sites, sending truck rolls to those sites to get either hardware or software problem fix are usually expensive. And therefore, it is important to improve the reliability and availability of those edge deployments. And in this work, we compare two different systems that build with different building blocks. One system is the server-based storage system that is built with the general purpose servers. And the other system is built with the it's called embedded storage system, and it is built with embedded storage devices. Since each embedded storage device is simpler and cheaper than the general purpose server, it makes sense to have more nodes in the embedded storage system within the same cost of power and space restriction. And also because each embedded storage device is essentially a file domain, and therefore the number of value domains in the embedded storage system could be much greater than the number of failure domains in a server-based storage system. Our hypothesis is that the more independent failure domains a failover mechanism spans, the more available the data becomes. And to verify this assumption, we design a metric called relative benefit, and which is defined by the ratio between the possibility of the data loss of the two systems. And you just need to remember that the greater the ratio, the better the embedded storage. For the actual mathematical model, you can refer to the paper that I cited in the previous slides. Because of time limitation, I just want to convey what we found from our evaluation. In general, we found that the higher resource aggregation of the general purpose server, the higher the relative benefit of embedded storage. The resource aggregation could be aggregating the storage devices or aggregating the computing resources in the server. And this result makes sense because aggregating more resources in the server essentially would increase the failure domain of the storage system. With this understanding, we can actually move forward to start to research some related and interesting questions, such as, in order to achieve simpler data availability, what are the benefits of the cost, power, and space of using embedded storage devices for storage systems? And now let's get into my second important piece in my research plan, which is the use of storage architectures. As you know, the resource availability is the main hurdle for the architectures for use of storage devices, and therefore we really need to look for architectures that can work with small and bound resources. Given our research experience on Ceph, we are planning to use Ceph as our first floating timing platform and try to add some modifications that can help limit and bound resources. And also, we would like our architecture can easily accommodate and leverage domain-specific hardware. For example, it could be possible to involve a small set of smart NIC and a user storage cluster, and use them dedicated for some data transformation tasks that for the data stored in some other storage nodes. And finally, we would like the users of storage devices not just be able to run fixed functions, but also be able to run dynamic functions. And the dynamic functions could created and parameterized by user clients. And because the complexity of those functions are usually not known beforehand, not just like the fixed functions, and therefore the storage vendor would not be able to pre-allocate enough resources to ensure some service level objectives, right? And so for the architecture, we really need to have a mechanism that allow functions to push back to the caller. So in order to allow the dynamic function to be executed within the storage devices, we would need a function execution framework. And there could be there are right now two popular frameworks would allow customized code or untrusted user code to be running within a sandbox environment. One of them would be the WebAssembly. This technology was originally provided to compile code that written in other programming languages other than JavaScript to be efficiently running within web browser. And because it creates a nice abstraction of different programming languages, the WebAssembly community would like to extend this abstraction to allow the program not just be able to call the web API, but also be able to call some system API and active with the system directly. And so the WebAssembly system interface, or WASI, is a direct result of this idea. And so with this interface, for example, if you compile the print function into the WebAssembly binary code and then run it on the runtime that is created for a native OS, and then the result of the print will go to the terminal of the system. Well, if you run the same binary code on the runtime that is created for the web browser, then the output of the print would go to the console of the browser. Another technology is called eBPF. And with this, this technology was originally created to allow users to inject customized code into the kernel such that it can deal with some tasks such as network packet filtering or the kernel function chains. And so because it's so efficient with this abstraction, people would like to leverage the same code and put it onto different domains. However, because the kernel source is licensed with GPL, but unfortunately there is another project which is called uBPF, and it has already created a user-space eBPF virtual machine. And right now, people can port and use the code and port it to embedded system to execute the eBPF programs. And here is an example. If you're interested, you can click on the link and see the people right now has already started to test embedding the eBPF virtual machine inside the QEMU storage device, and just to evaluate how would it be looks like if a storage device will actually be able to execute the eBPF code. And here I just want to compare these two different technologies. And on one hand, both of them require a virtual machine to execute the bytecode generated by the compiler, and both of them support JIT compilation to ensure the efficient execution. And for eBPF, the only programming languages that support to write eBPF code is the restrict C, which means you can only write bounded loop. You cannot use global variables. You cannot use floating point numbers. You cannot use constants, and you cannot even call functions reside within a shared library. And it also have strict limitation on the complexity of the function of the program. And on the other hand, the WebAssembly is far more flexible in terms of the type of programming languages to be able to compile into the WebAssembly bytecode. It supports C, C++, C#, and Python, and many, many more. And also for the security model, the goal of the WebAssembly is just to provide the developer with useful primitives while protecting users from buggy and malicious codes. And therefore, it should have much less limitation on what a programming language could do by using this technology. And also, more recently, the WebAssembly community has started to think about putting more functionality support, including the support of the multiprocessing and the direct memory management into the WebAssembly. And so finally, the final piece in my research plan is related to the network. And so if you still remember, the use of storage devices in the picture that I showed before is actually connected with a full crossbar network. And so the performance of the use of storage devices highly depends on the efficiency of the full crossbar network. However, to create and develop a full crossbar network that allow a large number of endpoints to be able to communicate at the maximum bandwidth at the same time may not be feasible. Therefore, we may need to explore network topologies that would allow efficient communication at larger scales. On the other hand, we also need to look for some network protocols that would allow to run within a low resource requirement. And in this context, the HTTP3 would be a good candidate because it is running on top of UDP, and it could be much more efficient than its predecessor, which is the HTTP2, and that is running on top of the TCP/IP stack. And also, the HTTP3 has solved the head-of-line problem. So, thank you. Now I can conclude my talk by saying thank you so much for listening of my presentation. And if you have any questions, please let me know.